PDF, CDF, WTF. Hey everyone, welcome back to another episode. I am Tino, aka The Dirty Quant. Today we're going to talk about transformations of distributions. This is something that I find in general it scares people because you're sort of putting numbers in, you get numbers out, and you're not really ever sure how it should really work. What should you be using when? I've tried to put together a really simple guide, and it should really help you along the way. All right, so there's this PDF which I'll link down below. Essentially, where you should really just start, in the middle. Are you simulating data or not? Right. So there's obviously. This is like the glue of statistics. These sort of transformations are really what sort of puts everything together and lets you really put things in a convenient format for various reasons. So look, I'm really big into sort of simulating, so these come in like really handy. So if you are simulating, you should start with, pick your poison, but a NumPy random.uniform hat is a great sort of starting point where you can generate uniform data. If you know the parameters you want to use with your target distribution, great. If no, go for the default. It doesn't really matter. Then, just follow here. Use your inverse CDF. Look, I know it's confusing. We'll have a practical example in the middle. I'm not going to go through all the little combinations here, but you essentially can follow this through and go, okay, well, what do you want to do with the data? What format the data's in, and follow this through. And then there's sort of the second page here where it shows you what space are each of these functions expecting the data in, and what space will they give you the data in. Space, I mean, like, does the data, is the data in the range of 0 to 1? That's sort of the space that I mean, right? If you say, look, this is expecting data to be between 0 and 1, you put it in this little magic box, cool, and it comes out from -infinity to infinity. Probably doesn't mean much to you, but we'll try and remedy that, and the same for the CDF and the PDF as well, right? Pretty straightforward. Look, inverse CDF, obviously you can see there's a relationship there. But let's actually fire up a notebook and transform some data, get some visuals out, and we will make you a master in just a few minutes. Fixing the random seed, doesn't matter, don't really have to. So right, I'm going to start off by generating some random uniform data using our friend NumPy, right? So what does that even mean? So this is what uniform data looks like. So uniform means that it's flat. There's nothing that happens more often than something else, right? So you can see at the bottom, it goes from 0 all the way to 1. And you're saying, well, Tino, look, it doesn't look very uniform to me. Well, I generated 1,000 samples. If I were to generate, I don't know, 100,000 samples, it would look a lot flatter, but I don't want to kill my computer. So let's just keep it at 1,000. Happy days. Just pretend that that's a straight line, right? So uniform, that's really our starting point, right? For a lot of statistics, this is a really good sort of starting point. I know that normal real life data doesn't look like this, but we'll get there in just a second. Cool, so I've got my uniform data. And let's say I want to generate data that is in the sort of, I don't really want to use the word normal because normal means something in statistics. So let's just use the word traditional or raw data, right? So let's say heights of people in the office. Look, I want to generate, what would it look like? People are in the office and their heights, right? So from here, I would use, my data is indeed in that space, 0 to 1, this is what my uniform random data looks like. And I'm going to use our friend inverse CDF, right? And it's going to output data from -infinity to infinity. You think, well, people are not -infinity tall or +infinity tall. Yes, that is quite correct. But let's sort of look at that. So look, there's a few sort of key takeaways here. You can use this, and CDF stands for Cumulative Distribution Function, and I can't spell. And it takes in data in that 0 to 1 space. Lower bound value is -infinity, upper bound is infinity. So it transforms a 0 to 1. So it's just a mapping function. It takes that 0 and makes it -infinity, takes the 1 and makes it infinity, and everything in between. What that CDF is up to you. You need to tell it, okay, this is the distribution that I'm seeking. most of the time, and this is statistics is really built on, is the normal Gaussian distribution, right? So this is what we're going to do here. So here, this parameter here, norm.ppf, which is the same as inverse CDF. It's really up to you. Percentage point function. I prefer inverse CDF, but up to you, right? Feed it in the data in the 0, 1 space, which we already have. And this is normal, so it needs a location and a scale. That's just the mean and the variance of it. So I'm going to have a mean of 160, and I'm guessing scale is variance 1. Okay, cool. So, and that's really it. So I'm going to generate some normal data and then actually plot it because we actually want to look at it. And that's sort of it. So now I have data which sort of resembles height. You got, I don't know, an average of about 160 centimeters, sounds about right. And we've got a few tall people over here, 180 centimeters plus, and a few sort of more compact people here on the left. And that's really what it looks like. If you say, look, I think that data is more skewed one way, it's got this sort of distribution, happy days, beautiful. Change that inverse CDF to a distribution that you think would suit whatever it is that you're targeting. It doesn't have to look like, doesn't have to be normal. World is your oyster as long as you have the inverse CDF function for it. So this is there's not one inverse CDF. Every distribution has a set of CDFs, PDFs, inverse CDFs. It's up to you to sort of put these together and transform data. And this is sort of not too dissimilar to what I did in the copulative video. It's really all based on this sort of stuff. There you go. Look, I started with uniform data that has no flavor, has no characteristics, right? And I've transformed it into what could potentially be, look, I've got 1,000 people entering my office or whatever it could be, right? And this is what their heights would be. So, where should I how high should I build the doors? I don't know, whatever example you want to do, right? So, and then you have some data that can go into your model and then can flow through, right? Happy days. All right. So what if I wanted to take raw data? So this, let's call raw data that you would sort of see in the real world. So this is sort of real people's measurements of heights, right? And I want to transform it into uniform data. Well, in this case, I actually use the CDF, cumulative distribution function. It expects data in that minus infinity to plus infinity. That's what the sort of bounds, and it will return to you something in the 0, 1 space, right? But if you use, yes, theoretically, minus inf, plus inf. Look, SciPy, I've seen it sort of stops at about minus 37 and plus 8. So it's quite a long way from plus and minus infinity. But those are obviously huge numbers. Essentially, think of them like standard deviations. Huge numbers, more than you'll ever need. So SciPy, thank you very much for your kind service. Yeah, lower bound 0, so the lowest number is going to spit out is 0 and the highest number is 1. Standard normal, again, it's like 90% of statistics can be served by that. There's this special symbol called phi. It looks like, I don't know, a circle with a bar going through it. And it's got this characteristic is that for the normal, because it's symmetrical, the minus a value, whatever it is, x that you're putting in, right? This is the input value. So minus infinity to infinity, let's call it, say, minus 3, right? It's going to be the same value as 1 minus phi of just 3 on its own, right? So it's got that symmetry. So sometimes you'll see these like, remember if we did stats at school, we had all those tables and stuff. This is all it is. It's just those tables are just transforming one input into sort of something else, right? So here, I'm going to input that normal this data, which is the data I had here with my heights, right? And then I'm going to push it through the CDF. In this case, you've got to know what the parameters are, right? So there's this little caveat is like, okay, what is the mean and variance of this data? Or sometimes you don't know, the data is like too complicated, but you can make an approximation. And there we go. This is the output, and this should look exactly the same as our initial data. So because I've passed it essentially through one process and then back in through the same process backwards, and it should look exactly the same. So if you do not know what the distribution of the data is, you don't know the parameters, right? Here we're making everything parametric, life is easy. But in the real world, you don't know that. So what do? You can use something called an empirical CDF, which just essentially just takes the data that you have and says, well, that lower number, I'm going to map it to 0. That highest number, I'm going to map it to 1, and then just going to smooth out the data in between. You do obviously need quite a few samples. It's not parametric. It's just sort of magic, but it does still give you data in that uniform, and you can use it as such, right? Happy days. And what about PDF? You hear this sort of PDF probability density function as well. How does it fit into all of this, and what are its characteristics? So it expects data in the minus infinity to plus infinity. Again, raw data, just normal measured data, let's just call it, and it will give you a value that's always above 0. Okay, so it's got this really close characteristic to the CDF. So the PDF, I'm going to say PDF, and it's the probability density function, is the derivative, essentially the slope, the angle of the CDF, and I'll show you just below what that looks like. So if the derivative of 1 is actually you can actually integrate and go backwards, right? So if you can actually obtain the CDF by integrating the PDF, which is like, okay, that's great, because look, PDF is good, but I think CDF are better, and it's actually easier to obtain the PDF. So there's no closed form solution. What does that mean? You hear this word, it means there's no nice formula that you can complete. But look, most packages behind the hood have some sort of transformation that essentially is taking care of you. So, you can actually get the CDF of the normal. That's what essentially has been done for us by integrating that PDF. Output's always bigger than 0, and the area under the curve adds up to 1. So let's actually look at what that looks like. And there we go. Cool. So let's just make the screen a little bit smaller. Sweet. So top left, inverse CDF, and on the x-axis I've got the inputs between, let's call them 0 and 1, and essentially map to a value on the output. So if I have 0.6, pop, I go here, my output is 0.2, and as I go higher and higher, I tend towards infinity. Obviously this doesn't go to infinity, my screen isn't that big. And here we have essentially its companion. As you can see, it's actually the flipped version of that, where you've got, let's just say, -3 to +3 on the x-axis. So that's like your normal measured data. And essentially, I like to think of a CDF as like filling up, right? Because it goes from 0 all the way to the top. And really, CDF tells you what's the probability of you observing a number smaller than this, right? So 0, let's just say this is symmetrical, like this area down here, right? And we said that the PDF and the CDF, this one at the bottom, this one top right, they're related. If I go to 0, you go, well, what's the chance of observing a number smaller than this? So to the left, let's just see if I can draw. Nope. Let's see if I can, yes. What's the number, essentially what's the area under the curve right here? And that's what the CDF gives you. So I can go to 0, go up, see where they meet. Let's just say that's close enough, 50, right? So essentially 50% of the numbers are smaller than that. If I keep going higher and higher and higher and higher and higher, let's say, essentially 3 is my limit, right? Just for this plot, 99% of all observation are going to be smaller than that. Let's just say, okay, wealth, you've got, I don't know, Bill Gates at one end, right? So Bill Gates would sit up here, because you could say, how many people are poorer than Bill Gates? And you go, well, 99.x, whatever percent. Essentially, pretty much everyone is to the left of his wealth. And that's really what the CDF is. You can think of it as like, lining everyone up, smallest to biggest, and then cutting it at some point and going, well, how many people are to the left and right? And because of that property, and especially this property that we said here, especially for this one here, because of that symmetry, we can start to sort of say, okay, well, what's the probability of, how many people reside in this chunk? Let's say this is, let's say this is people's wealth, actually, this distribution down here, right? So the -3, they're actually net debt. So they got -$3, and the people here got +$3. So you go, well, what's the proportion of people that have between $0 and $1 of assets? So I could take, essentially, I want to measure that area here, right? And this is what we always did at school with those tables, but I found them very confusing. And, you know, to measure that area here would be very hard, but all I need to do is go to my friend CDF, go to 1, go up and measure up, and that's going to be 0.84. So 84% of people have less than $1 worth of wealth. And then I can go to the 0 and go, oh, that's, let's just say, a half. So it's going to be roughly like 30% of all people sit in that area there. So 30% of all of my sample have between $0 and $1. And that's sort of pretty much it. So it sort of makes, I guess, in practical terms, the PDF a little bit redundant, because you go, well, I can't really, the number that comes out here, you can't really use for anything yourself. This number here, if I just had to have one thing, you know, I would have just a CDF, because I could flip it, get the inverse CDF, happy days. It's a number. It's a transformation that makes sense to a human, but this doesn't. The PDF doesn't actually make sense to you. Where the PDF really comes in is if you find the log or natural log, you know, ln, and if you find the log of the function, you can use in what's called the log likelihood. And then when we're trying to find parameters, you know, in which function generated it, and this is where it comes into like things like optimizers, and they use something called like maximum likelihood estimation, or you can use it in MCMC, which, you know, I'm a big fan of. And that's where the PDF comes in, because I'm just going to feed it values and it's going to return to me higher or lower. It's sort of playing like Marco Polo, you know, when you say, you know, hotter, cooler, you know, Marco Polo, you know, am I getting close to the parameters that generated this data? And that's what the PDF can tell you, right? And it's, you know, it's really, really powerful. Definitely a story for another day, but that's sort of pretty much it. You know, have a look at this notebook, have a look at this. This is a very simple guide here. You know, what is my data? Which format's my data in? Is it like in raw data? Okay, cool. So I'm probably going to be using the CDF, right? Great. I want to transform it into, say, something that's a 0 to 1 to just know, is this a big number, a small number? I guess you could use like a Z-score if you want to do that and just transform into something small or big. But the nice thing about transforming it into that uniform 0 to 1 is then you can use another distribution to transform it into something else, right? So you've got your data in one format and then transform it into something else. You can start to simulate from it just because you've got something that's like a common language. So pretty handy. Hope you found that useful. It's a great introduction. I think this is like the key foundation to stats, and knowing these, understanding, okay, what number good. Look, play around. You know, get the CDF. You know, so if you get the CDF and play around, so you know, just get some code. Go away, Cortana. Right. So we said, oh well. If I put a number, it expects a number in which space? Minus inf to inf. What if I put -1? What number comes out? Okay, 15. What if I make it -5? Okay, starts to become really, really small. Okay, what if I make it, I don't know, 1? Right, what if I make it bigger? 3. Okay, starts getting really close to 1. What if I make it, cool, so you got, you know, putting 7 here, we've got sort of like the Tres Comas clubs, if you know that reference, right?
This is my own brand, Tres Comas.
So, okay, so this essentially, think of it as like standard deviations or, you know, whatever from our data, like pretty much all of it's going to fall below that. And if you get into these extreme numbers, something's usually up. One thing I don't like is when people start to say, oh, this was a 10 standard deviation event. It's like, well, it probably wasn't a 10 standard deviation event. It's very likely that you're measuring it wrong, because you just shouldn't be observing data, you know, once every, you know, collapse of the universe in like billion years time span. So there's probably some things up with your data, and we like to obviously use parametric data to make our life easier, but sometimes it just doesn't work. Bill Gates does not sit on the distribution of people's wealths, you know, because he's just he is a 20 standard deviation or more sort of wealth. So it's probably not the right way of measuring it, right? That's it. All right. Hope you enjoyed the video. And this video today, we achieved 1,000 subscribers. So thank you very much, whoever you may be. The channel is growing, and thank you everyone to keep watching. We've got some really exciting things coming up. and I'll keep you posted. All right, cheers. Bye.